Kirchhoff's rules, sometimes referred to as Kirchhoff's circuit laws, are a pair of rules used typically to analyze DC circuits. The first rule that we'll examine is Kirchhoff's junction rule. The junction rule states that the sum of the currents flowing, and yes, I know that current flow is a bit redundantly redundant. Anyway, the sum of the currents flowing into a junction is equal to the sum of the currents flowing out of said junction. Mathematically speaking, current in equals current out. Sounds simple enough, right? Let's take a look at a circuit diagram for a junction to elucidate this rule. We'll take a simple three-way junction and label it J1. We'll draw current flowing into J1 from the left, call it I1, and current flowing out the right leg and down the vertical leg, I2 and I3 respectively. How exactly did we decide the directions and labels for these currents? We'll address this very good question momentarily. So applying the junction rule to J1, we have current in, that's just I1, equals current out, which is I2 plus I3. And that's it. That's how the junction rule is applied to a junction. Before we move on, I'm impelled to point out that Kirchhoff's junction rule is just a consequence of a more physically significant principle, namely the principle of conservation of charge. So we can sort of think of J1 as a fork in the road where the charges, either continue traveling to the right or turn and move downward. Got it? Good. Now let's examine Kirchhoff's other rule, the loop rule. The loop rule states that for any closed loop, the sum of the voltage lifts is equal to the sum of the voltage drops. We'll define a closed loop as any continuous path in the circuit which ends where it started. The loop rule stated mathematically is the net voltage for a closed loop equals 0. Okay, now let's look at a simple circuit to see how we apply the loop rule. Here we'll have a voltage across the source, V sub S, and a voltage across the resistor, V sub R. Since it's a simple circuit, we'll have a singular current, and its direction of positive charge flow is clockwise, due to the orientation of the voltage source. Next, we'll label our circuit loop, loop A. Note that for most circuits, currents and loops won't coincide, and need to be explicitly labeled separately. Okay, to apply the loop rule to loop A, we'll travel clockwise around the loop summing voltages. Starting on the bottom left, we'll have positive V sub S, a voltage lift, and then moving around to the other side, we'll have negative V sub R, a voltage drop. We set that equal to 0, and that is how we apply the loop rule. By the way, Kirchhoff's loop rule, like the junction rule, has its physical roots in a conservation law, namely the principle of conservation of energy. Okay, now let's discuss the conventions associated with Kirchhoff's rules. The first two conventions relate to the loop rule in identifying voltage lifts and drops. If we're moving around a loop and we travel through a battery while summing voltages, and we go from low to high, which is to say going from the negative terminal to the positive terminal, then the voltage of the battery is treated as a positive voltage, which we'll call a voltage lift because of the increase in electrical potential. If instead we travel through a battery high to low, that is positive to negative, the voltage is treated as negative, which we'll call a voltage drop because of the decrease in electrical potential. So for voltage sources, low to high, we have a positive voltage. High to low, we have a negative voltage. It turns out that the sign of the voltage across a resistor also depends on the direction of our labeled current. So if we follow a current while summing voltages through a resistor, then the voltage across the resistor is negative V, or invoking Ohm's law, negative I times R.
Drop!
If instead we oppose the direction of the labeled current as we pass through the resistor, then the voltage across the resistor is treated as positive I times R.
Lift!
So for resistors, follow the current, negative IR. Oppose the current, positive IR. Now, a lot has been said about the directions of currents and loops. How are these directions initially decided? This is the best part. The directions of loops and currents are assigned and labeled arbitrarily, with absolutely no preference in direction. So long as the circuit is correctly analyzed, using Kirchhoff's rules, the actual direction of positive charge flow will be revealed in our results. So it's kind of like choose your own adventure in physics land.
Physics land!
One final convention relating to labeling our circuit diagram. Typically, we'll use one more loop than the number of junctions in the circuit, so be sure to have enough of them labeled before applying Kirchhoff's rules.